today we're going to apply derivatives to something called related rates problems. So related rates, you're going to have some quantity, and as one thing changes, something else changes. So that's what the related rates is. So the steps for solving. Read the problem carefully and pay attention to the rate that you are trying to find. And that should be pretty obviously stated in the picture, or in the problem. Drawing a picture, if necessary. Some don't require it, but a lot, the picture is helpful. Identifying the variables, assigning symbols to them, and then identify the rates of changes as derivatives. You're going to write an equation that relates the variables. It may be necessary to use more than one equation. Then you're going to differentiate both sides of the equation with respect to time, and substitute the numerical values for the variables and the derivatives, and then solve for the unknown rate. All right, this will all make a whole lot more sense once we actually do some problems. So first problem, a circular region is decreasing at a rate of 2 pi square inches per minute. When the area of the circle is 25 pi square inches, how fast is the radius of the circle decreasing? So this example is a good illustration of as the area changes, that means the radius is changing, and that's what we're going to investigate. So we have a circle, and its area is decreasing, which will then result in the radius decreasing. So first thing I'm going to do is identify what I have. So it says the circular area is decreasing at a rate of 2 pi square inches. So we're going to call this dA dt. The rate of the area with respect to time is decreasing, so we'll make that a negative 2 pi. The area of our circle is going to be 25 pi. And what we're looking for is how fast the radius is changing. So then we write an equation that relates our variables. In this case, the area formula for a circle, A equals pi r squared. Then I'll take the derivative with respect to time. So dA dt is going to equal, we'll use the power rule here, 2 pi r, and then times dr dt. So it's an implicit derivative with respect to time. Now I'm going to fill, so there's two ways to now approach this. Either you can fill in the values and then solve for dr dt, or you can solve for dr dt So you can either solve for the variable or plug in the values. So I'm going to plug in the values that we have and solve for our unknown. So dA dt is going to get replaced with negative 2 pi. R, we don't really know, but we can find it. So this is the information we have. So we're looking for when the area is 25 pi, what's the change? So if area is pi r squared, that means my r at this moment in time is going to be 5. So my r is 5, and what we're solving for is dr dt. So everything should have a value filled in except for the one thing that you are solving for. Then we'll just do our algebra here. So 2 pi equals 10 pi times dr dt. So my dr dt is going to equal negative 2 pi divided by 10 pi, which is going to be a negative 1/10. And our units, if it's square inches per minute, this is going to be inches per minute. Next one, given x squared plus y squared equals 169, find dy dt. If dy dt equals 5, when x equals 5 and y equals 12, find dx dt. So we're going to take the derivative of this with respect to time. So that's going to be 2x dx dt plus 2y dy dt equals the derivative of a constant is just 0. So we'll fill in what we know. So 2x is 5. Dx dt is what we're solving for. Y is 12, and dy dt is 5. So we have 10 times dx dt plus 2 times 5 is 10 times 12 is 120. So 10 times dx dt equals negative 120. So dx dt is going to equal negative 120 divided by 10 is a negative 12. Okay, number 3. Let x and y be functions of time that are related by this equation, y squared equals 2 plus xy. We are given time is 5, the value of y is 3, dy dt is 6. We're going to find value of dx dt at time equals 5. So I'm going to take this equation and find its derivative. So we're going to have 2y dy dt. Derivative of 2 is 0, and then I'm going to need to do the product rule. So I'm just going to do x prime y plus y prime x. So in this case, x prime is going to be dx dt. Y prime is going to be dy dt times x. So we'll plug in our knowns and solve for our unknown. So 2y is 3. Dy dt is 6. That's going to equal, we're solving for dx dt. It's still 3. Dy is still 6. X is not, but we do know what y is. So I'm going to go to my original equation here, substitute in 3 for y, and solve for the x. So 3 squared equals 2 plus x times 3. So 9. 7 equals 3x. So x equals 7/3. So we'll replace that for our x here, and then solve for dx dt. So 2 times 3 times 6 is 36. This will be 6 divided by 3 is 2 times 7 is 14. So then we'll subtract that. Times 3, and then divide by 3. So dx dt equals 22/3. Okay, our next problem. If the radius of a sphere is increasing at a constant rate of 1 centimeter per second, find the rate of change of its volume when the radius is 6. So I'm going to define all my constants here. So the radius is changing at a rate of 1 centimeter per second. So dr dt, it's increasing, so this will be a positive 1. The radius is 6, and we are solving for, so find the rate of change of the volume. So then we have an equation that relates these variables. So the volume of a sphere is 4/3 pi r cubed. Then we'll take the derivative. So dv dt is going to equal, using the power rule, 3 times 4/3 is 4, pi r squared times dr dt. So we're finding dv dt. Our knowns are 4 pi 6 squared times 1. So we multiply all that together. To get 96 pi, and this would be centimeters cubed per second since we're talking about volume. Have another sphere problem. The radius of the sphere is increasing at a constant rate of 2 centimeters per minute. So dr dt equals 2. At the instant the surface area becomes 64 pi, so SA equals 64 pi. Find the rate in cubic centimeters per minute at which the volume of the sphere is increasing. So we are trying to find, I'm going to put this down here because we need to use this, dv dt. That's what we're trying to find again. My equation is still going to be 4/3 pi r cubed. So dv dt is 4 pi r squared dr dt. The rate of change of volume is what we're trying to find. 4 pi. We don't have the radius at this point in time. We have the surface area. So I need to use this formula to arrive at the radius. So the formula for surface area of a sphere is 4 pi r squared equals 64 pi. So I can divide both sides by pi and 4. So r squared is going to equal 16, which means my radius that we're going to plug into the equation is 4. And dr dt is 2. This one, then just simplify this down. So if we multiply 4 times 16 times 2, we get 128 pi. This is volume, so centimeters cubed per minute. Okay, this one's a real classic related rates problem. So it says, consider a 13-foot ladder leaning on a wall. Suppose that the top of the ladder slides down the wall at a constant rate of 3 feet per second. What is the rate of change of distance between the bottom of the ladder and the wall when the top of the ladder is 12 feet from the ground? So here's our wall. Here's the ground. And we have a ladder that is a constant 13 feet. Okay, so this thing is sliding down, which means this is going to be sliding out. Okay, so we're not told variables. It's not as obvious as like when we have volume and radius and we just use those. So we're going to choose some variables, and I'm going to choose this distance as x and this distance as y. So let's go through this. It says the top of the ladder is sliding down the wall at 3 feet per second. So we're going to say dy dt is going to be a negative, since it's moving down, 3. Okay, we are trying to solve for how far the distance is between the bottom of the ladder. So we're trying to find the rate, dx dt. That's what we're solving for. when the ladder is 12 feet from the top. So at this point, y is going to be 12. So what can we use in this situation? What formula relates the things here? So the things I have are the sides of a right triangle. So the formula I'm going to use is good old Pythagorean Theorem. Okay, so x squared plus y squared equals 13 squared. And we don't plug in the y at this point in time because at different values, x and y are both changing. Y is getting smaller, x is getting bigger. So we'll take this derivative, 2x dx dt plus 2y dy dt equals 13 squared is 169, doesn't matter. Its derivative is 0. So I need to fill in my information here. The variable I didn't solve for yet is x. But if y is 12 and the hypotenuse is 13, 12 squared plus x squared equals 13 squared. That means x is going to equal 5. So we're going to have 2 times 5 dx dt is what we're solving for. 2. My y is 12. My dy is a negative 3. And that equals 0. Okay, so here 10 times dx dt. If I multiply these, negative 3 times 12 and 2, I get negative 72. So I'm just going to add that over to the other side and then divide. So dx dt is going to equal 72 divided by 10, or 7.2. And it should make sense that this is positive, since if this is decreasing, this would be increasing. And this would be in feet per second. A rectangular swimming pool, 10 meters long and 5 meters wide, has a depth of 3 meters on one end, 1 meter on the other end. If the water is pumped into the pool at a rate of 0.3 cubic meters per minute, at what rate is the water level rising when it is 1.5 meters deep at the deep end? So we're going to need a picture. Okay, so I'm just going to take a cross-sectional view. So we have a swimming pool that has a deep end and a shallow end. Okay, the pool is 10 meters long, and then you can draw, it's going to be 5 meters wide. It has a depth of 3 at the deep end and 1 on the shallow end. Okay, so let's look at the information we have. The water is being pumped into the pool at 0.3 cubic meters per minute. So that's actually going to be the change in volume. The rate of change of volume is 0.3 meters cubed per minute. Okay, at what rate is the water level rising? So we're interested in this dimension. So I'm just going to call that dh dt, the height, when the water is 1.5 meters deep at the deep end. So that's going to be 1.5. All right. So I'm going to start with the equation, and then we're going to have to go back to the picture to get some more information. So we're writing a formula for the volume of the water. Okay, so the volume of the water is going to be, so it's going to be at 1.5. So let's say this is 1.5. So if it's 1.5, it's halfway up here, which means it's not actually going to touch here. So I'm looking at this area here, which is going to be 1/2 base times height. I'm going to call this B, I'm going to call this H, So 1/2 the base times the height times the width, which is going to be 5. Before we do this, what I need to do is get this all in terms of one variable. And since I'm looking for dH dt, I want to get this entirely in terms of height. I can do that by looking at similar triangles. Okay, so what I want to know, okay, the height and the base. So along here, up until we get to where it reaches the shallow end, the similar triangle, let me try to draw this on top here, is going to be that there. So let's look at the dimensions. So this top dimension here is going to be 10. This dimension, since it goes right up to this edge, this is 10. This is going to be 2 because this is 1, so we take 1 off here. So this triangle is 2 to 10. So I can come up with a ratio from similar triangles. So base over height is going to equal 10 over 2. So I'm going to solve for B is going to be 5 times H. So over here, I'm going to have 5/2. My base is now 5H times H. So we're going to have 25 over 2H squared is my volume. Now I'll take the derivative, so dV dt is going to equal 25/2 times 2 is 25, H dH dt. Fill in what we know, which is our volume is increasing at a rate of 0.3 when the height is 1.5. We're trying to solve for dH dt. dt, when all is said and done, is going to be 0.3 divided by all of that, which you can dump right in the calculator, is going to be 0.008. This would be in meters per minute. Okay, a conical tank with the vertex down has a radius of 8 feet at the top and is 15 feet high. If water flows into the tank at a rate of 16 cubic feet per minute, how fast is the depth of the water increasing when the water is 8 feet deep? So again, a picture is going to be helpful. Okay, so here's my cone. I know that the height of this thing is 15, and the radius at the top is 8. So let's look at our knowns and our unknowns. So the 8 and 15 we labeled on the picture. The water flows into the tank at 16 cubic feet per minute. So again, dV dt is going to be 16 per minute. How fast is the water increasing when the water is 8 feet deep? So I'm going to call that height is 8, and we are solving for dH dt, how fast the water is increasing if the volume is increasing. The volume of a cone is 1/3 pi r squared h. Just like the last one, I need to get this in terms of the variable I'm interested in, which is h. So I need to use this information to come up with the relationship there. I'm going to, again, use similar triangles because it's always going to be proportional as you move down the cone. So 8 and 15, r and 5. So I'm just going to do r over h equals 8 over 15 and solve for r. So r is going to be 8 15 times h. So I'm going to substitute that back in up here. Okay, so my volume, we're going to have 1/3 pi 8/15 squared is going to be 64 over 225 h squared h. So if you multiply this and this together, and you can use the calculator to help you out, we get 64 over 675 pi h squared times h is h cubed. Now we take the derivative, dv dt is equal, if I multiply this by 3, we get 64 over 225, which makes sense since we multiplied by 3 to get there. Pi h squared dh dt. So 16 equals 64 over 225 pi. My height was 8. dh dt is what we are solving for. Okay, so we're going to take this and divide it by all of this. So dh dt is going to equal 16 times 225 over 64 pi 1 over 64, however you want to write that, which if you simplify this is going to be 225 over 256 pi, or if you wanted just an approximation, that would be 0.280 feet per minute. And that's what our dh dt is equal to. A 6-foot-tall man is walking at a rate of 2 feet per second towards a streetlight that is 15 feet tall. At what rate is the length of his shadow increasing? Or changing? It will be increasing. So our picture, we're going to have a 16-foot tall tower, or light post. Okay, so we've got a 6-foot tall man, a 15-foot tall light, and it's going to shine the light here, and this is going to be the length of the shadow. So I'm going to call this S. If you want to use a better variable than S, then by all means do it. Okay, so he's walking away. So this distance here, I'm going to call X. So what we are told is the rate he is walking towards the street light. So he's going this direction. Is going to be, I'm going to call that dx dt. The distance from here to here is changing. So since he's walking towards the light post, this distance is getting shorter. So the dx dt is going to be a -2 feet per second. So we need to write an equation that relates all of this information. Okay, so what I'm going to do is set up a proportion with the similar triangles. All this geometry you never thought you'd use again. So here I'm going to do 6 over s equals 15 over this distance is going to be x plus s. Go ahead and simplify this down a little bit before we do the derivative. So I'll cross multiply. And it's an s, not a 5. So again, if you want to pick a different variable, go ahead. So I'll subtract. So 6x is going to equal 9s. So x equals 9 divided by 6 is, actually we should go the other direction. I'm going to divide by 9. So S is going to equal 6 divided by 9 is going to be 2/3 x. And I did that because what I'm actually looking for in this case is ds dt. You can do it the other way. It's just, you know. So I take the derivative. So ds dt is going to equal 2/3 dx dt. Fill in my knowns to get what I'm trying to find. So ds dt is going to equal 2/3 times dx dt, which was -2. So this will be a -4/3 feet per second. Okay. Last example. A man 2 meters tall walks horizontally at a rate of 1 meter per second toward the base of a tower 25 meters tall. When the man is 10 meters from the base of the tower, at what rate is the angle of elevation changing if that angle is measured from the horizontal to a line joining the top of the man's head to the tower? So again, a picture is necessary. All right, so let's say I have my 25-foot tower. And somewhere we have a man who is 2 meters tall, and he's walking towards the base of the tower. I'm going to call that x. So we have that dx dt, he's walking towards the base, so that distance is going to be decreasing, so we'll make that negative. Okay, and we're looking for what rate, let me say, and x is 10, when x is 10. We're looking for when the angle changes. So the angle that we're referring to is this angle here in the picture. So since this is 2 and this whole thing is 25, this side is going to be 23. This side is still going to be x. This distance isn't going to ever change. So let's write an equation. So what relates x and theta and 23? That would be tangent. So tangent of theta is going to be a constant 23 over x. We're in this problem trying to find d theta dt. All right, so let's take the derivative. So derivative of tangent is secant squared theta times d theta dt is going to equal, this is going to be -23 over x squared times dx dt. So I'm going to actually solve this one step before I fill in the values. Okay, I can divide by secant. Since secant is 1 over cosine, that means I'm multiplying by cosine. So this is going to be -23 over x squared times whatever dx dt is times cosine squared theta. Okay, so we've solved for d theta dt. So we have -23 over x we're given is 10. Dx dt is -1. Cosine squared theta. So we're going to go back to the triangle. So when this is 10, this is 23. Cosine of theta obviously is adjacent over hypotenuse. So my cosine theta. My adjacent side is still going to be 10. The hypotenuse, I'm going to have to do the Pythagorean theorem. So for the hypotenuse, say h squared equals 10 squared plus 23 squared. So h is going to be the square root of 629. So cosine theta is going to be 10 over the square root of 629, which means cosine squared is going to be 100 over 629. So that's my last piece over here. So cosine squared is 100 over 629, and then we multiply all that through. Okay, so when you use the calculator, you get 0.0366. Now this is d theta dt, so we need the units for theta over the time units. The units for theta in calculus are always going to be radians. So this is going to be radians per second. So that's how we do various related rates. You're going to have a lot of different types of problems, so just thinking it through, organizing the information you have and what you're trying to find, and then go from there.